laid down by the Greeks, famously Euclid in his Elements, formulated axiomatically what we still teach at school as the geometry, the Euclidean geometry. And as you probably know from school, there are 4 axioms, and the 5th one about parallel lines that somehow stood apart, and mathematicians for more than 1,000 years tried to do something with it to no avail until the 19th century, where came first the realization that you can actually construct geometries that are not constrained by this postulate of parallel lines from Euclidean geometry, and you can create other types of geometries that were given the name non-Euclidean. But it also created towards the second half of the 19th century this kind of unhealthy situation when different people worked on different geometries. It was not clear actually how to define a geometry and how they're related to each other. So it was clear that some kind of new approach, a paradigm shift was necessary, and this new idea came from Felix Klein in 1872. So he was also one of the founders of what we nowadays call group theory, and he proposed the radically new concept of considering geometry from the perspective of group theory. So essentially considering geometry as a definition of a space plus some group of transformation that acts on geometric shapes and then study their properties, asking what kind of properties remain unchanged or invariant under these transformations. And famously, this new idea that entered the history of mathematics as the Erlangen program was given in a talk that he was requested to give his inaugural lecture at the University of Erlangen, where he was appointed as a professor when he was only 23 years of age. So that's, I think, even by modern standards, is quite remarkable feat. So basically what he showed is that if you consider the classical Euclidean geometry, then it arises from the Euclidean group. So you study invariance with respect to rigid motions, translations, rotations, and deflections, but you can make the group larger. You can consider, for example, affine or projective transformations. And he also was the first one, together with Eugenio Beltrami, who managed to unify different non-Euclidean geometries that existed at that time, in particular hyperbolic geometry. That was the first non-Euclidean geometry that was constructed. So this idea was really transformational in geometry. It took quite some time to unify it with Riemannian geometry, about 50 years. But it also had a very big impact on mathematics in general, more culturally, but also on the field of physics, where in the beginning of the 20th century came the realization that you can apply the same principles, the idea of symmetry and the idea of invariance, to actually derive the laws of physics from these foundations. And famously, the theorem of Emil Neuter, who proved that you can derive conservation laws mathematically. For example, conservation of energy, that before that was only an experimental law, could be derived from the symmetry of time. And these ideas appear to be very powerful, so Weil himself proposed what was called gauge invariance, that evolved in theoretical physics to what we nowadays call the standard theory, and this is more or less how we understand physics today. So there are a few things that do not fit into this picture, but physicists like distinguishing between external symmetries of the space-time, right? So what is called the Poincaré group that gives rise to the Minkowski geometry of the relativity theory, and the symmetries of the quantum fields that give rise to different forces or different interactions of particles. And it was formulated very strongly and very laconically by Philip Anderson that it's only slightly overstating to say that physics is the study of symmetry. So you can ask the question, of course, what does it have to do with deep learning of graphs, or deep learning in particular? And the answer is that we have a similar situation to what happened to geometry in the field of deep learning. So many different neural network architectures that were developed or emerged in the last decades from different considerations, or for different types of problems, or for different types of data. Like convolutional neural networks were conceived for image analysis and computer vision. Recurrent neural networks were developed for time series and temporal data analysis, and so on and so forth. And apparently there is no unifying framework or common denominator to these methods, and this is one of the reasons why deep learning is considered kind of collection of tricks and hacks rather than a real science. So we try to challenge this picture by providing a unifying framework in the spirit of the Erlangen program, and this is what we call geometric deep learning. So trying to use principles of geometry to analyze, to derive new architectures, and if you consider the machine learning problem in the simple setting, right, supervised learning, you can think of it, some synthesists would say, so this is just glorified curve fitting, right? So it's a function interpolation and extrapolation problem, right? So you can view it from the standpoint of approximation theory as you're given a function, right? And you are given a few samples of this function. So think of classical example of classifying cats and dogs, right? So we have high-dimensional inputs, the images of these animals, and then a function that outputs 1 or 0, right? And you can try to represent this function to capture it for some black box, and for decades we know what we can put in this box, right? These are artificial neural networks, like this one, the perceptron, that was developed already in the 50s by Frank Rosenblatt, and we know about these architectures that they are universal approximations. So if you just connect 2 layers of perceptron, you can approximate any function, any continuous function to any desired degree of accuracy, right? So basically, it can represent a very wide class of functions. Now, of course, if you come from the perspective of approximation theory, you can say, wait a second, but I have infinitely many functions that I can pass through a finite number of points. So what mathematicians usually do in these cases, they introduce some assumptions about these functions, which are called regularity, right? So you want some kind of nicely behaving functions. And in approximation theory, there are standard classes of regularity, such as Lipschitz continuity. The problem with these kind of standard notions of regularity is that they don't scale well with dimension. So if I give you very well-behaved functions, Lipschitz continuous functions, and I start increasing the dimension, right, and ask the very simple question, how many samples do I need to take to achieve approximation error of epsilon, you will see that very quickly the answer will grow bigger than the number of particles in the universe, right? So it is exponential in the number of dimensions. And in machine learning, unfortunately, we need to deal with very high dimensional problems, so even very tiny MNIST images are almost 1,000 dimensional, right? So basically, the number of, in the example of cats and dogs, the number of cats and dogs that you will need to see or to show to the neural network will be more than the number of atoms in the universe. So there are not sufficient number of animals around to do this training. So, and you can also see it that somehow we throw away, if we treat images just as high-dimensional vectors, we throw away a lot of structure, because if I show you this example of a digit that is shifted by just 1 pixel, if we just treat it as a vector, it changes dramatically as input into the simple-minded neural network. And we need to show a lot of examples of shifted digits in order to train the network to recognize it as the same class, right? And this is what we call, in modern deep learning terminology, data augmentation. So what happened in the 70s or early 80s was a new class of architectures that were the first, you could call them geometric architectures, that initially were inspired by neuroscience, such as the neocognitron of Fukushima, and then famously the classical architectures, convolutional architectures of Yann LeCun, that use the idea from the way that the neurons in the brain, in the visual cortex of the human brain, are connected to do what is, again, in deep learning terminology, is called local weight sharing. So you don't have a fully connected network, you have weights that are shared across the image, and it was motivated again by these problems of object recognition, that no matter where the object is located in the image, you still want to recognize it as the same class. And this fits into this blueprint of geometric deep learning, because we don't need to treat images as high-dimensional vectors, we need to treat them as data that lives on some low-dimensional geometric domains, such as grids or planes, in this case, of images. And then we can describe the structure, the geometric properties of the domain through a symmetry group. And the symmetry group, in this case, is the group of translations. It acts on the data that lives on the domain through some representation. So in case of images, it's just a shift operator. And then we have functions that take as input these signals living on our geometric domain, and these functions must respect the symmetry in some way. And this some way will be what we call invariance and equivariance. I guess in yesterday's keynote of Max Welling, we heard more about this. So I will not go much into more details, but this is the general blueprint. So we have a domain, a symmetry group that is associated with it, signals that live on the domain, and the corresponding representation of the symmetry, and then functions that are either invariant or equivariant with respect to this group. And you can see that convolutional neural networks are one example, right, where the group is translations, and then convolution is actually a linear operation that is equivariant with respect to translation. So you can define convolution axiomatically, so you can discover convolution from these basic constraint of symmetry, that's the only linear equivariant that emerges from the translation symmetry group. Another example that would be interesting for us today, talking about graphs, are graph neural networks. So graph neural networks operate on domains that have graph structure, and there the group that is associated with the graph is the permutation group. It comes from the fact that we don't have canonical ordering of the nodes of the graph, and then as we'll see, the permutation equivariant or invariant functions are implemented through message passing. And you can see that this principle of geometric deep learning can be applied to different domains, whether it's graphs, whether it's meshes, or whether it's more general homogeneous spaces, or some maybe more exotic things like manifolds and other geometric objects. And you can show that many known architectures that are popular in the domain of deep learning can actually be derived from these foundations. So not only that, but this blueprint also allows you to create new architectures. One of them, for example, equivariant transformers or equivariant graph neural networks that have become extremely popular recently in the context of protein design, like AlphaFold from DeepMind, or molecular modeling. And again, I think Max mentioned it in his talk yesterday. So we'll be talking about graphs, and I don't think that I need to convince you, this audience, that graphs are interesting. They are a very ubiquitous mathematical abstraction for systems of pairwise relations and interactions. You can apply graphs to model things from very tiny scale, like molecules, to very large scales, like social networks. And the problems that we can consider in the context of learning on graphs are of three types. These could be graph regression or graph classification. So I give you a graph that, for example, represents a molecule, and I would like to predict its physical or chemical properties. So this is a very typical problem in virtual drug screening and drug design. So you want, instead of doing experiments in the lab, you want to do them on a computer. You can do node classification. So again, in social networks like Twitter or Facebook, you would like to, for example, predict which users on the network are behaving badly, like spammers, for example. So you would like to assign some labels to these nodes. And then the problem of link prediction, so you want to infer whether two nodes should be connected by an edge in the graph. And again, recommender systems in social networks and other applications are a very prominent example. Now, what are graph neural networks? Essentially, these are parametric functions that take in a graph with some features and produce some output. And again, the output can have the same structure as a graph, so it could be node-wise output, or it could be an output for the entire graph. And the way that these graph neural networks are implemented, there is a zoo of different architectures, but roughly we can distinguish between these three flavors. So the first one that we call convolutional, by analogy to convolutional neural networks, where the way that this function is defined is by, for every node, aggregating information from the nearest neighbors. And this aggregation depends only on the structure of the graph. So basically what I'm doing in convolutional graph neural networks, I'm, for example, averaging the information from my neighbors, and then maybe every neighbor node features can be transformed by some learnable function. So it reduces to the classical convolution when the graph is structured as a cube. Slightly more general flavor of graph neural networks are attentional graph neural networks. So again, think of averaging your neighbors, but now the weights do not only depend on the structure of the graph, they also depend on the features through the attention mechanism. So I can decide which features should be contributing more or less. Right? And the most general case is message passing. So every node sends a message to every other node, right? So I'm collecting information from my neighbor in a way that is conditioned on who I am and who my neighbor is. Right? So it's a general bivariate function that depends on the features of both nodes. Now, there is a deep theoretical link between graph neural networks and graph isomorphism tests. So if you don't know what graph isomorphism is, it's essentially saying that two graphs are structurally the same. So I can find an edge-preserving bijection between their nodes. So in other words, if I look at the adjacency matrices of the graphs, because I don't know the canonical ordering of the nodes, I can permute one graph into another, so that the adjacency matrices are the same. And it has been an important problem in graph theory from the 50s or 60s. And Weisfer and Lemon, two Russian mathematicians, came up with an algorithm that initially they believed to be a polynomial time solution for this problem. We actually don't know what is exact complexity of graph isomorphism test, but basically they came up with a test that allows to to determine whether two graphs are isomorphic or not in some cases, and it was shown relatively recently in the context of graph neural networks that message passing graph neural networks are equivalent under some technical assumptions to the Weisfeld lemma test. So they are at most as expressive as the Weisfeld lemma test. And this is an important factor because you want to know what kind of functions you can represent by message passing graph neural networks, right? So some functions, for example, cannot be represented, and there are many examples because of this equivalence. You know that certain things cannot be computed by message passing. So here is an example of two graphs that are not isomorphic. So these are actually two chemical structures, so these are two molecules. And they are not isomorphic, yet they cannot be distinguished by the Weisfeld graph isomorphism test. So again, allow me not to go into details what the graph isomorphism test does. It is an iterative color refinement procedure, so it starts with the nodes of the graph having the same label or the same color, and then it studies the structure of the neighborhood of every node. So you can see that initially in these graphs, every node is of two types, so it has either two neighbors or three neighbors. If you apply an injective function to this information, to this collection of neighbors, then you get you can distinguish between these nodes. Then you can repeat the procedure again. Now we have three types of neighborhoods, right? And these become three distinct labels. And at some point, the color refinement stops, and you can produce a distribution of these colors. And you see that in this case, the distributions are the same. So the algorithm is constructed in a way that if the distributions are different, you know that the graphs are not isomorphic, but if they are the same, you cannot determine. So this is a necessary but insufficient condition for graph isomorphism. So what it gives in theory, right, that basically there is an equivalent between message passing graph neural networks and the isomorphism test. So it gives you a way of measuring the expressive power of graph neural networks. But in practice, as we've seen in this example, there are some non-isomorphic graphs that cannot be tested by the Weisfeld lemma test. And also, it appears that some graphs might be unfriendly for message passing. Right? So if I need to send information from one block to another and they're connected by this narrow bridge, information might be lost on the way, and this results in problems that we'll discuss towards the end of the talk that are called oversquashing. So the first problem is addressed by, for example, designing more powerful isomorphism tests. So there is an entire hierarchy of WL tests, and there are equivalent constructions of graph neural architectures that mimic these kind of higher order color refinement schemes. For the second problem, you can try to decouple the input graph from the computational graph and do what is called graph rewiring. So you change the connectivity to facilitate the propagation of information and make the graph friendlier for message passing. So we'll talk about what exactly should be done in order to do it. Okay, but what it creates a gap between theory and practice, because the underlying assumption of classical graph neural networks is that we are given the graph as an input and we use exactly the same graph to propagate the information. And by analogy to the Weisfeld lemma algorithm, we know that we can discover certain structures, maybe there are some ambiguities, but that's what is done in classical GNN. In modern architectures, you do more. So you can say that, for example, you can introduce some extra features, what is called positional structural encoding. So this is commonly done in transformers. You can, for example, lift your graph into a high-dimensional topological space. So consider, instead of graphs, for example, cellular or simplicial complexes, you can consider a graph as a collection of subgraphs that are extracted using some policy, and this allows you to use analogies to what is called deconstruction conjectures in graph theory. You can also introduce symmetry of the data that lives on the nodes of the graph. So this is common in molecular modeling, where the graphs are geometric graphs. So they live in Euclidean space, and we have continuous symmetries of the coordinates of the atoms of the molecules, right, of the nodes of the graph. And then it can be equivalent not only to the permutation of the nodes, but also to the, for example, special orthogonal group that rotates and translates this molecule. And finally, if the graph has special structure, then you can reduce it to the classical convolutions. So basically, the common denominator of these methods is that you either make up or you introduce from some side information more structure into the problem. On the other hand, you can say that you want to change the graph, right? And in the extreme case, you can say that you disregard the graph altogether. So you can throw away all the edges and consider only the nodes, consider them as a set. And then you can design architectures that work on sets. So these are called, for example, deep nets, deep sets or point nets, right? And these are now classically used in computer graphics for the analysis of three-dimensional point clouds. On the other hand, we can say that instead of making every node be unable to interact with other nodes, you can allow every pair of nodes to interact, right? So you're now assuming that the graph is complete or fully connected, and then you learn the right graph for the downstream task through the attention mechanism, for example. And this is how transformers operate, right? So transformers are a special type of graph neural networks where the graph itself is latent and you learn it as you train the neural network architecture. So the graph rewinding method that I mentioned before sits somewhere in the middle. So you start with some graph, but you want to make some changes into it. And it's a good question how you actually want to modify it. So we'll try to answer this question from a different perspective that comes from physics. And if we consider graphs as a special case again of this geometric deep learning grouping, and consider it to other similar geometric domains, like grids and meshes, right? So grids are special types of graphs. Meshes are what is called simplicial complexes, so they're graphs with some extra structure. You can see that even the way that you aggregate information is very different in all these three objects. So on a grid, I don't have any ambiguity of the order of my neighbors, right? So I can designate the neighbors in a fixed way. So I can say that I have a top neighbor and the bottom neighbor and the right and the left neighbor, so the order is fixed. On the mesh, the situation is slightly different, so I can say that I can designate the first neighbor, right, like this node number 1, and then I can order all the rest of the neighbors in, for example, clockwise orientation. So meshes are discrete manifolds, they are locally Euclidean. But then the choice of the first neighbor is ambiguous, so everything can be defined up to cyclic shift, right, or a rotation. And on the graph, as we know, everything is defined up to permutation, so any permutation of the nodes is possible. So in a sense, graphs have the least structure out of these three different objects. Now, another thing that you can also notice immediately is that you can consider grids and meshes as discretizations of some continuous domains, right? So grids are discretizations of planes, and meshes are discretizations of surfaces or two-dimensional manifolds. We don't have immediately this nice analogy in case of graphs. And what we will try to do in the next half an hour approximately is to come up with a continuous analogy of models for GNNs. And this will be the physics-inspired graph neural networks, which is the main topic of this talk. So what I invite you for the next remaining part of the talk to think of graph neural networks in a different way. So we'd like to think of them as dynamic systems. So imagine that every node of the graph is a particle and it lives in some high-dimensional space, right? So the space is the space of features that live on the nodes of the graph. And then they follow some trajectories, right? So there is some system of differential equations that governs the behavior of these particles, and they also interact with each other, right? And these are the trajectories that they might follow here. So basically, GNN models a dynamic system. The layers of a graph will be just discretization of the time, right? So I have a continuous time variable. I can sample it, for example, at fixed time steps and say that these are layers of graph neural network. What is a graph? So you can think of graph as a coupling function. So basically, when we discretize the system of differential equations, each row in this large matrix of features will represent a node in the graph, and then the rows are relate to each other. So there is some kind of interaction, so they don't evolve independently. So a graph is a coupling function, and as we'll see, in some cases we can also think of a graph as a discretization of some continuous space, same way as we discretize geometric domains in classical PDEs. So if we consider different types of evolution equations that can drive this kind of dynamic system, so probably the first thing that comes to mind when we think of propagation of information in some domain is a diffusion equation, right? And the diffusion equation was probably one of the first physical phenomena that was rigorously studied mathematically by none less than Isaac Newton in a famous paper that was published anonymously in the Transactions of the Royal Society in 1701. He would become Sir Isaac 4 years afterwards. And basically he described an experiment that he conducted using a self-made thermometer and a mathematical model that shows how hot objects change their temperature, or what he called heat at that time, which is nowadays an incorrect term, in time. And what is nowadays called the Newton law of cooling tells you that if you introduce a hot body in some environment, then the temperature a hot body loses in a given time is proportional to the difference of the temperature between the object and the environment. So the bigger the contrast, the faster it will, the rate of temperature change will be. So the way that you can describe it for other stuff as well, right? So it can be diffusion not only of temperature, it can be diffusion of some chemical substance, of concentration of some compound. It can be also diffusion of things like, for example, wealth or opinion, right, or rumor. So it can be really very abstract and can be defined also in different domains. So this is how a diffusion equation might look like on a graph. So basically what we have here is a discrete version of Newton's law of cooling written in differential form. So what we have, here by x is the feature of every node, right? So think of it as temperature. So the temporal derivative is the rate of temperature change, right? So instantaneous infinitesimal rate of change. The xi, right? The feature of that node I will be the temperature of the object itself, and then the weighted average over the neighborhood will be the temperature of the environment, right? So that's exactly what Newton tells us how heat propagates locally. Now, if I slightly change the notation here, so if I rewrite this summation in a different form, what we see here reminds very much the classical diffusion partial differential equation that we know from the basic course in calculus. So what is written here is the graph analogy of the gradient operator, right? So it just takes the endpoints of an edge and it looks at the difference between the features at the corresponding nodes, and the summation over the edges that emanate from a node is the analogy of the divergence operator, right? So you can think of it in terms of calculus or tensor calculus. Then what a gradient does, it takes a function that lives on the nodes of the graph and makes it into a function that lives on the edges of the graph, and the divergence, which is an adjoint operator, goes in the opposite way, right? So it takes a signal that lives on the edges and goes back to the nodes. So combined together, the divergence of the gradient is called the Laplacian operator. Depending on the references, it could be defined either with plus or a minus, and basically it measures how different you are from your neighborhood, right? So basically it compares yourself to your environment, and that's why it is a very prominent operator that appears more or less everywhere in mathematical physics, from quantum mechanics to classical mechanics to wave equations to diffusion equations, you name it. The Laplacian is ubiquitous, so it's a very important. Need to compare yourself to your environment. Now, the heat equation that is written here, right? So this is the very basic, very simple form of the heat equation, right? So your instantaneous change in the quantity that you're measuring, like the temperature, is equal or proportional to the Laplacian of your function, and it is also a prototypical example of what is called the gradient flow. So if you're not familiar with the concept of gradient flow, I'm pretty sure you're familiar with the concept of steepest descent. So that's a continuous version of steepest descent. So basically it's an evolution equation that goes in the negative direction of a gradient of some energy that I denote here by this calligraphic E. And the energy that is associated with the heat equation is the Dirichlet energy. So the graph, this is how it looks like. So it's basically it looks at the norm of the gradient of some function on the nodes of the graph, right? And it measures the smoothness of the node features, how different you are from your neighbors. If you're similar to your neighbors, then it means that the graph, the signal on the graph is smooth, right? And the Dirichlet energy is decreased by this evolution equation, so it decreases along the flow. And in the limit, if I take the diffusion time to infinity, it results in all the features being the same on the nodes of the graph, right? So basically, the Dirichlet energy in this case will be 0. It means that I'm equal to my neighbors, right? And in graphical networks, this is considered usually an undesired phenomenon. This is what is typically referred to oversmoothing. So if you look at it as our dynamic system, these particles moving in high-dimensional space, it means that they will all collapse into a single point eventually in the limit. But it's not necessarily a bad thing, right? So what you can do, if, for example, if you make some assumptions about the data that lives on your graph, in particular what is called the Moffel assumption, that you're similar to your neighbors, at least mostly, then you can do a very simple thing without invoking any learning. So if you have, for example, a transductive setting where you have the labels of some nodes and you want to infer the labels of other nodes, you can do just what is called label propagation. So it is a diffusion equation with some boundary conditions. So I fix the labels of the known nodes as a boundary condition, and then I allow them to diffuse over the graph. And this works remarkably well if the graph is homophilic. If the graph is not homophilic, then it's not sufficiently interesting, and then you need to do more sophisticated things. You need to come up with more interesting architectures. So again, if we take a step back and look at graph neural networks from this perspective, from the perspective of dynamic systems, then the traditional stance would be to start with the evolution equations, right? Discretize the evolution equations, and then say that every iteration of a numerical solution of this discretized evolution equation, instead of having the iteration fixed, I want to make it parametric, right? And this is what is done, right? So this corresponds to a layer of a neural network, and you parameterize every layer, and you try to learn in the usual way these parameters of every layer. Now, what we are trying to advocate here, and this is what we call the gradient flow framework, or graph for short, is to start with the parametric energy. So you parameterize an energy, and then you derive the evolution equations as a gradient flow. So this automatically constrains or restricts the class of evolution equations that you can consider, because not every evolution equation is a gradient flow, so you need to have some energy that corresponds to it, and you need to minimize this energy, so you have a very particular form of the evolution equation. But what it gives you some constraints about the choice of the architecture, right? So basically it allows you to make educated architectural choices, because now you will be able to prove certain properties. So this is what I call interpretability. I know that this is probably a kind of a bad word in machine learning, because people understand it in different ways, but what I mean here by interpretability is that you will be able to guarantee that certain things happen or not happen in your neural network architecture, unlike a general architecture which can do more or less whatever it wants. So here's one example. So this is an example of a totally heterophilic graph. So here the node colors represent the labels. So we have a binary situation here. We have red and blue nodes, and the positions of the nodes represent these toy two-dimensional feature space. Right. So again, this is a dynamic system. The evolution equation that you can then discretize and get a graph neural network moves these nodes along certain trajectories. And the goal here is to classify correctly the nodes of the graph, right? And you can see that it's totally heterophilic, so it means that the blue nodes have all red neighbors and vice versa, right? And you can see that there exist trajectories that completely separate these two classes of nodes. And what you can show that if you consider a special type of energy, so this is a generalized version of the Dirichlet energy, that basically you diffuse information and you also allow mixing in this space of features, right? So what is called channel mixing. So it's a convolutional type architecture in the sense that the way that the mixing works, or the way that the information is diffused on the graph, is dependent only on the structure of the graph, not on the features. So that's why we have the adjacency matrix here and not the attention. So basically this process is driven by essentially the structure of this matrix that models the interactions in the feature space, and we have two types of interactions, of attractive type and of repulsive type, that happen along the positive and the negative eigenvectors of the channel mixing matrix W, and you can see them here, right? So there is the vertical direction is the direction of attraction, and the horizontal direction is the direction of repulsion. So the corresponding evolution equation looks like this, and again you can see that this is a convolutional architecture, like GCM. Actually, Max Welling was the author together with Thomas Kipf of this famous architecture that is now ubiquitously used as probably one of the simplest graph neural networks. And somehow the folklore says that it doesn't work in the case of heterophilic graphs. So, and usually the motivation that is provided is that what it does essentially is some kind of averaging of your neighbors, right? And this is the low-pass filter of the graph. So if the graph is heterophilic, it will mix incorrectly irrelevant information, and we show that this is actually not true. So very simple linear graph diffusion with channel mixing, what would correspond to a convolutional graph neural network architecture. If you appropriately choose the matrix W, in particular it has to be symmetric, so this comes from the constraint of the gradient flow, and it has to have sufficiently large negative eigenvalues, can provably avoid oversplitting. So basically you will not collapse into a single point, you can get perfect separation like what is shown here. So again, the main motivation for this, to study this framework, and you can ask why do I need to consider graph neural networks from this maybe slightly strange perspective, is to be able to prove statements of this kind. And here's an example of how it works in homophilic and heterophilic settings. So if you have a graph that is homophilic, then it looks more or less like what is shown here on the right. So this is an artificial example where we can control continuously the homophily of the data on the graph. And you can see that, for example, classical GCNs, the architecture of Kipf and Welling, it works very well when the graph is homophilic, but then it becomes worse than completely disregarding the graph using just multi-layer perceptron on the nodes when the graph is heterophilic. So indeed, as the folklore is saying, it doesn't work well in heterophilic settings, but still remaining in the class of convolutional type graph neural architectures, by correctly choosing the channel mixing matrix and the way that the architecture is structured, you can work well in this setting as well. So that's a kind of mild interpretability, right, or some theoretical guarantees that you can provide by approaching these architectures from the right perspective. So I talked so far about homogeneous diffusion processes, right, that correspond to the convolutional architecture. So let's look at slightly more interesting diffusion equations, and again, the motivation, let's visualize it on images. So this is the standard homogeneous diffusion equation. By homogeneous, I mean that the way that diffusion works is the same at every point of the domain, right? So this is how it will work on an image. So I start with an image, the face of Sir Isaac Newton. I diffuse it in time, and this is what I will get, right? So starting with initial condition, I can actually show that on a grid. What will happen is that we can describe the solution of the heat equation as convolution with some kernel that looks like a Gaussian with standard variation that grows with time, right? So this is how the kernel of this equation will look like, right? So a Gaussian. Now, this is obviously not desired, right? So you don't want, when you, for example, are denoising an image, you don't want to throw the structure of the image that comes in the discontinuities between different colors together with removing the noise, right? And the idea that came in the 90s, starting from the seminal paper of Pietro Peronna in Gita and Dramatic, is to consider a nonlinear diffusion equation where you can control locally the rate of diffusion or the diffusivity function in a way that is proportional to the norm of the gradient in the image, so the discontinuity, right? And basically what you want to do, in other words, is not to diffuse across edges. So if I have pixels of similar color, I can average them, but if I have on one side of my kernel I have white or bright pixels, and on the other side I have dark pixels, then I want not to mix them together. And the kernel will look like this. So these are called bilateral kernels, and the way to introduce it in the diffusion equation would be, for example, as this edge indicator. So the diffusivity is locally controlled by the strength of the gradient, right? And if the gradient is strong, you slow down or stop the diffusion. And this produces much nicer visual with the examples. And these kind of ideas gave rise to an entire field that evolved in computer vision image processing in the 90s and the 2000s of variation on PD-based image processing of computer vision. And it's been a popular field. There were conferences organized, books written, thousands of papers. It was all wiped out by deep learning. And the reason is that even though mathematically the idea is very appealing, so you define an energy and you write the diffusion or whatever evolution equation that minimizes it, and basically you can guarantee that you converge to the minimum of this energy eventually. The problem is that it is very hard to handcraft an energy that will somehow represent what should be done in your problem. And deep learning allows you to basically to tune parameters of these complicated parametric systems based on the data and the task that you want. So we can reinvent or adapt these ideas to the modern setting, and in particular, this is how non-homogeneous diffusion would look like on a graph. So now the diffusivity is not constant, so now it's a parametric function, and basically it takes the form of attention. It might need to have a special structure if you want it to be a gradient flow, and then if you discretize this non-homogeneous diffusion equation, replacing the temporal derivative with forward difference, so this is what is called forward Euler discretization. Under some extra assumptions, what you get is the graph attention network, the GATT, the famous architecture that is also very popular in learning of graphs. So you can see that also you can go beyond convolutional architectures, so you can interpret other classes of graph neural architectures as special instances of diffusion equations. Now, I promised you that we wanted to consider continuous models of graphs, right? And so far what we discretized was the time. So we replaced the layers with a continuous time variable. But if again we take a step back and look at, for example, how diffusion equations are solved on the plane, so you start with a continuous object, you discretize it as a grid, and then you need to discretize your differential operators, right? The Laplacian operator in particular in the diffusion equation. And here are three examples of how this discretization might look like, right? Or any convex combination of these discretizations is also a legitimate discretization of the Laplacian because it's a linear operator. So my point here is that we don't have really a canonical discretization of the spatial derivatives or a canonical graph that we can use in this setting. So there are ample choices. Of course, there are some numerical considerations, how fast it converges, what is the error order, and so on and so forth. But basically, there is a lot of freedom. So we want to adopt the same mindset to our setting of diffusional graphs, right? Which is kind of weird, almost a heresy, because you say that I'm doing diffusion on a graph, but I want to change the graph, right? So I don't trust the graph. And this will bring us to this concept that you can actually, and you want to change, or in some cases you must change the graph to do propagation of information in a better way. So now instead of considering the nonlinear diffusion that we've seen before, we can consider a non-Euclidean diffusion. And by non-Euclidean diffusion, I mean, and again, I make an analogy from the domain of image processing, I now consider the image as a manifold that is embedded in a joint space where we have feature coordinates and positional coordinates. So to make this example concrete, if you have a color image, RGB image, it will be a two-dimensional surface in R5, right? So every pixel has the X, Y positional coordinates as well as the R, G, and B feature channels, right? So in total 5 dimensions. This space actually doesn't need to be Euclidean, but from the fact that you place this manifold in this space, this is what is called an embedding, it induces a certain metric on this manifold. So it's a Riemannian manifold that comes with a special pullback metric, and you can define a diffusion equation on this manifold using a special definition of the Laplacian that is called the Laplace-Beltrami operator, after Eugenio Beltrami, one of the early Italian differential geometers. And this, what is called Beltrami flow, right, this special diffusion equation is actually a gradient flow of a generalization of the Dirichlet energy that is called the Polyakov functional. It is used in high energy physics in string theory to describe how bosonic particles behave. So if you apply this idea to a graph, basically now we consider a graph where every node has both feature and positional coordinates. So this is again common in graph networks to attach some positional coordinates to the nodes. And then now we have an evolution equation that involves both parts of these coordinates, both the features and the positions. And the evolution of the features is the standard feature diffusion. The evolution of the positional coordinates, you can think of it as a kind of implicit or soft form of graph rewiring, because if in the positional part of the space the nodes come closer together and there is no edge between them, you can introduce an edge artificially to facilitate the flow of information. And likewise, if nodes drift apart, then maybe you can say that they don't need to communicate directly to each other. So long story short, this is how it might look like. So this is an example of, again, a toy problem of node classification on a citation network that is called Cora. So the colors here represent the features, encoded as R, G, and B. The positions of the circles represent the positional coordinates, right? Every circle is a node. And you can see that both the features and the positions evolve by this Beltrami flow, but the graph is also changing, so we are rewiring the graph on the fly, right? And you can see that we are distinguishing here nicely between these 7 clusters, which are the classes that we want to find in this data set. And if you think of it, again, if you consider it from maybe the straight mindset of signal processing, so what we have here is some kind of filtering process that is happening on some data that lives on the domain, but the domain is changing under our feet. So we are applying the filter, but the domain is moving, which is quite a disturbing picture if you think of it from the traditional perspective of signal processing and machine learning, but it's actually a very common perspective in geometry, and geometers like to take a domain, a manifold, and subject it to some cruel form of evolution. For example, one famous type of evolution equations for manifolds are Ricci flows. So Ricci flow, what it does, it evolves the metric of the manifold, so that's the local structure, in a way that is proportional to its curvature. So if you look at actually this equation, it looks very much like the diffusion equation. So we have the temporal derivative of some quantity, right? So in this case, it's the metric tensor. And on the right-hand side, we have a second-order derivative that is kind of similar to the Laplacian. So structurally, you can think of it as a diffusion of the metric, but of course, the properties of this equation are very different. What it does to a manifold, if you start with something that looks like a dumbbell that has negative curvature in the middle and positive curvature on the sides, by running Ricci flow, that it will become more like an ellipsoid and then become more like a sphere and then collapse into a point. And the reason why these kind of weird evolution equations were introduced with the idea of using this technique to prove the Poincare conjecture. Because what Poincare conjecture, as you probably know, it's a famous result in topology that tells you that you can characterize spheres by the ability to collapse a closed curve into a point. So the conjecture was that it works beyond 2 dimensions, right? So on the 2-dimensional sphere, you can always do it, but if you have a torus, for example, a closed curve that goes across the donut, I cannot collapse it into a point, right? And as you probably know, topologists were told that a differential geometer proved their Holy Grail theorem, Perelman, using these techniques of Ricci flows. So what does it have to do with graph neural networks? As I mentioned, in graph neural networks, we have this situation when the graph is such that message passing fails to propagate information properly on the graph. And this typically happens when the volume of the graph grows very fast, right? So in some graphs like trees or small world networks, the number of the neighbors of the neighbors of the neighbors, right, what we can define by analogy to volume on continuous domains, grows exponentially fast. And if we have a task that requires long-range interactions and the graph has this unfortunate structure, we have a phenomenon of oversquashing, which means that information somehow is lost on the way because it's entangled with a lot of features of other neighbors, right? So you can see that basically it's a mixture of two things. So we have the contribution of the graph topology, right? So for example, the fast current grows, and also the long-range interaction. So this has to do with the task. So let me start first with the topology and then talk about the task. So the topology, basically what we can do is, if we assume a message passing graph neural network of certain type, allowing to skip these assumptions, basically we make some assumptions about the number of layers, right? So the depth, the width, the smoothness of the activation functions and so on. Basically, I can characterize oversquashing in the following way. So it's a kind of insensitivity. So I make a perturbation in the input in some node, and I see how this perturbation is felt at the output of the graph neural network at some distant node, right? So how efficiently the information is propagating from one node to another. And you can measure it by a partial derivative, what is called the Jacobian, and if you look at the norm of this Jacobian, you see that it's small, it means that you have a low sensitivity problem or oversquashing, right? So you can define oversquashing in this way. In our paper, we show that you can bound this Jacobian by some constants that depend on the model, right, on your neural network architecture, like the depth, the width, the bound on the parameters and so on, but also something that depends on the graph topology. So here we have a power of the normalized adjacency matrix. So you see that the structure of the graph plays a role, but it's not clear how exactly, right? So we would assume that it is, for example, in more benign graphs like grids, probably will not see oversquashing, and in more pathological examples like trees, maybe it will be more acute, right? So we need something more nuanced than just looking at the power of the adjacency matrix. We want to be able to distinguish geometrically between something that looks like a grid and something that looks like a tree. And that's exactly where curvature enters into the play. So same way as you can define curvature on a manifold as a kind of geodesic dispersion, so you send geodesics from adjacent points and you see if they converge, diverge, or remain parallel, right? And this allows you to distinguish between something that looks like a sphere, a hyperboloid, or a plane. So here we can look at nodes that are adjacent, connected by an edge, and edges emanating from these nodes, and count certain number of structures, triangles, rectangles, and so on, and see, for example, if they tend to form triangles, then we locally look at something that looks like a click. So that would be the analogy of a sphere, right, the positively curved part of the graph. If they form rectangles of certain types, then these will look locally like a grid. And then if they drift apart, then it will look like a tree, right? The analogy of hyperbolic or negative curvature. And define it in a certain way, right? Define for every edge of the graph. This is what we call discrete Ricci curvature. We can actually relate the curvature, this local geometric characterization of the graph, to oversquashing, and we show, again, in the same paper, that strong negatively curved edges contribute to oversquashing. And this also gives rise to a way of rewiring the graph by removing these negatively curved edges and replacing them with edges of higher curvature by doing something that resembles, at least philosophically in principle, a discrete version of the Ricci flow. So basically we can do graph rewiring, we can make the graph more adapted or better suited for message passing by doing this kind of evolution. Now the problem with this approach and other approaches that are common in literature for graph rewiring is that they disregard the task altogether, right? So far I told you that I can relate the graph topology to overscorching, but it doesn't consider the task, and the task is very important, probably a good way to visualize it by considering a graph that models a molecule, and as you probably know in chemistry and physics we have different types of forces or different types of interactions. So how deep the architecture is, how the bound on the weights of the layer, the smoothness of the activation functions and so on, as well as the graph topology, how friendly the graph is for message passing, and then the given task is quantified through the mixing. And we can come up with bounds, for example, bounds on the weights or bounds on the depth. So allow me to skip the details. Basically, here are the different definitions. What it gives you this kind of almost obvious statements, but quantified in a precise way, is that weights need to be large enough to allow sufficient mixing for a given task, right? And if I give you a task, I can actually tell how big the weights need to be, and also the depth must be sufficient for given mixing. And unfortunately, here the results might be not very optimistic because we see that depth must be of the same order as the commute time. So commute time is a graph theoretical construction that measures the reachability of one node from each other. So basically what will be it's called commute time because I can look at the random walk that goes from one node, passes through another node and comes back, and the expectation of these random walks measures how reachable two nodes are in a graph. So actually many graph rewiring techniques, you can show that they try to reduce the commute time, so they try to improve the reachability and the connectivity of the graph by introducing extra edges or maybe cutting out problematic edges. And you can also show that in some graphs the pessimistic upper bound is something like the cube of the number of nodes, so it can result in impossibility statements. So you cannot have the number of layers that is and cube, the number of nodes to the power of 3. And this is a kind of new way of characterizing the expressive power of graph neural networks that doesn't resort to the more popular Weisfeld-Lemon formalism. So you can say, for example, that informally for a message passing neural network with a certain number of layers, these message passing neural networks cannot run a task that requires mixing of certain high mixing among features at nodes with large commute time. So basically it connects the property of the task and the property of the graph. Right? So basically you can relate the expressive power and of an architecture to both the structure of the graph and the function that you have on this graph. So the last thing I want to talk about is slightly different concept, which we call delayed message passing. And if you think of what we've seen so far, basically different flavors or different type of graph neural network architectures, they define what information is exchanged between nodes, right? So in other words, for example, how you transform your neighbors, right? By what we've seen in gradient flows, that you need to mix the channels in a special way with certain attractive and repulsive directions, right? Or maybe you can use attention, right? So that answers the question what. Graph rewiring tries to solve the question where, right? So when I have information in a node, to which other node should I send it? Should I send it to my direct neighbor, or maybe I should introduce an extra edge, right? So send it indirectly. What doesn't come immediately to your mind is also the fact that, as we've seen, it's a dynamic process, right? So it has some time dimension. So it is also very important to consider when to send this information, when to introduce it. So it's not only just sending everything, right, and determining what kind of information is sent, but it's also very important to say when this information is introduced. And if you compare, let's say, classical message passing architectures and transformers, and let's say that I need to pass information from the red node to the green node, in classical message passing, you will take 3 steps, right, of message passing, or 3 layers of the graph neural network to send this information, because that's the distance between these 2 nodes. So it will take propagation first to the neighbors, and then to the neighbors of the neighbors, and then to the neighbors of the neighbors of the neighbors. And you see that this information gets entangled with the features of other neighbors, right? So it doesn't arrive purely to this target node, it is mixed with other stuff. In a transformer, on the other hand, because I have a complete graph, so at least in principle, all the nodes are accessible at every layer, right? So I can send information directly, but that might be too much, right? So I'm flooded with information, so it might be too hard to learn how to use this information properly. So what we are suggesting is dynamic rewiring with delay, so we can introduce this information not immediately like in a transformer and not gradually as in classical MPNNs, but we can introduce it in the form of geometric skip connections. So we will send the information to the node when it should appear there, when it would have arrived in a normal message passing architecture. But we introduce it directly as a skip connection without having it entangled with information of other nodes. And we show that this way we are able to outperform graph transformers on certain tasks that require long-range interactions. So I think it's a big debate in deep learning community whether transformers are the kind of universal architecture. So this is probably to some extent the case also because of what is called the hardware lottery, so that you can implement them efficiently on the GPU. But I would say that in types of problems like in chemistry and biology, when the data is scarce, you don't have this luxury that you can throw infinite amount of data and infinite amount of compute at this generic architecture and learn everything from the data. You need to work smarter. This is one of the ways of how to make transformers also more efficient because they're sparse. So I think I'm out of time, so let me finish here. So what we gained from this physics-inspired perspective on graph neural networks. So first of all, I think it gives a new way of considering problems like oversmoothing, bottlenecks, overscorching, and so on. You can explain old architectures, which is always nice, right? So you want a new theory to explain the old stuff and motivate why it has been done. So it can potentially give rise to new architectures, for example, considering different solvers or different type of evolution equations. So I didn't show it here. I talked about diffusion, but you can consider also, for example, combination of wave equations with diffusion equations, so oscillatory systems with dissipation, also maybe quantum mechanical systems. You can also make principled architectural choices. So we've seen it in the example of gradient flow, right? So it constrains the choice of your architecture and your parameter, and it provides some theoretical guarantees. There are deep links to maybe other tools for mathematics or topics that are probably less known in the field of graph neural networks and maybe ML in general, such as differential geometry and algebraic topology. And again, we didn't talk about algebraic topology, but you can basically you can lift the graph into some more interesting exotic objects such as cellular sheaves and do diffusion equations there, and this also gives you a way of quantifying the expressive power in a different way. You can also, we also talked about graph rewiring, and one of the primordial scenes of graph neural networks is that they use the same graph to propagate information, so they don't decouple it from the computational graph. And in many cases, the graph is not good for message passing, so you do want to change the graph to make the propagation better. And again, this kind of physics-inspired and geometric techniques give you precise tools to quantify whether the graph is good or not, considering the task and considering the architecture and the structure of the graph. And finally, if rewiring answers the question of where to send information, then introducing also the temporal dynamic component in the form of delayed message passing also gives you control of when to send this information, and this potentially gives rise to a new architecture that is more flexible than transformers and also a superset of message passing architectures. So I will stop here. Thank you very much for your attention.
Thanks a lot, Michael, for this very interesting talk. So for the questions, please line up there and there. There are 2 mics. Just stand up and go there if you have any questions. So I think there's already the first one.
Yes, thank you for the talk. It was quite broad overview over everything in GNNs. I was wondering for the last proposed model, the time-delayed rewiring, how does that affect the expressive power of GNNs? It seems like it would maybe increase the power by 1 degree, but I'm not quite sure.
Yeah, so we have some theoretical. We didn't look too deep into it, so we show that it's a superset of the standard vice-fair element equivalent message passing. So potentially it can be more expressive. But again, we didn't analyze it, so it's still an open question of how more expressive.
Thank you. Please, next question from that side, maybe.
Thank you for your great stuff. I would like to ask about the concept of rewriting again. So, one of the power of using graphs in your computations is that they encode domain knowledge very efficiently. So, the concept of rewriting is only computational, or can have some implications on the domain that the graph has been created? Can it generate new domain knowledge, for example, or refine the domain knowledge that exists?
Yeah, so it's a very good question, Roland. I try to give some answers to it. So the graph is both computational device and part of the input, right? So it is important part of the input. So basically what the graph neural network tries to do is it tries to approximate some function that depends both on the features and the structure of the graph, right? And it tries to do it by message passing on either the same or a different graph. So the extent to which you can do it is, for example, can be quantified through this notion of mixing, and then you can decide whether your given graph is good or bad for this task, right? That's obviously not the only way of doing it, so there are probably many other ways of doing it. But I think the important point is that you cannot completely disregard the graph because it carries important information. How important this information depends on the function that you're trying to compute. How good this graph is for message passing also depends on the task, on the function that you're trying to compute. So it's kind of, everything is entangled together.
Please, for the next question.
Thank you for the talk. I think it's very interesting to see all these physics ideas coming into machine learning. My question is actually a bit more from the physics perspective. Like, if you give a physicist a dynamical system, like you have these graphs as dynamical systems, I think one of the first questions they ask is like, what are fixed points? What are there limit cycles? And have you looked into these kind of things and maybe see like different architectures make different trade-offs between this? Or
yeah. No, this is a good question. But one example is exactly this phenomenon of oversmoothing. So that would be a fixed point, right? So everything converges into some state that might not be interesting in some cases, right? So it could be interesting in others. So this is what we try to avoid. So for example, we can show that certain architectural choices induce high-frequency dominated dynamics that avoid this kind of fixed point. It might converge to a different fixed point that is more interesting. So same thing with diffusion on cellular sheaves, for example. So you basically a cellular sheaf is a kind of a non-Euclidean version of propagation on the graph, where you also transform the features when you compute the gradients in a certain geometric way. And then the diffusion has more interesting properties or more interesting fixed points. So the kernel of this equation is richer than just, for example, a constant factor that you see in the standard diffusion equations, which gives you a way of analyzing the expressive power. For example, how many node classes can you separate? So yeah, basically, to answer back to your question, the fixed points are very interesting.
Maybe one more question from this side of the room. We are a bit out of time. Maybe try to ask quick questions. And I think already the coffee break has started.
I will try to answer briefly.
Yeah.
I think I talked too
It's
much.
okay, please.
Thank you for the highly informative talk. So my question is that I was wondering if you can draw connections between physics by GNNs and causal representation learning.
Yeah, so I'm not an expert in causal inference, but there have been some works. So Thomas Kipp, for example, that I mentioned in relation to GCNs. So one of the ways of learning the latent graph could be in the context of causal inference. So you try to learn a graph that represents causal relations. So there are some works that are being done. So for example, in biological applications, one of the authors is Caroline Uller from MIT. And many others, Sholkov. So there are definitely connections.